In this video, I'm going to talk about error analysis for Euler's method. Euler's method, like any numerical method, isn't going to give us an exact solution. There's going to be some error between our computed solution and the analytic solution. And it's useful to know the magnitude of that error. And in this talk, we're going to talk about a method that we can use to quantify that error and understand Euler's method a little bit more deeply. So before I get into explicitly Euler's method, I'm going to start out by just talking about types of error that appear in all numerical methods. So the first type of error is what we call round-off errors. And this error comes along from the fact that computers don't store an infinite number of digits. And you probably know this from using a calculator. If you do a calculation in slightly different ways, you might get slightly different answers. And that's due to round-off errors. And it's the fact that the computer only stores a limited number of digits. For example, a double precision number, which this is the default that's in MATLAB. Stores 16 digits. So if you do a calculation in MATLAB, you store in 16 digits, which means that you have 16 digits to work with. It means you can have a number like 1.5832466, that's not a 667, where we have 16 digits here, and then we get to our last digit, whatever it is. And the total here of all these digits is 16. And we can also have an exponent. So at the end of this number, we might have e to the 34th. So we can represent very, very large numbers and very, very small numbers, but you will only have about 16 digits to work with. So keep that in mind. In most applications, it doesn't really come into play, but in some situations it does. The second type of error that does come up often is what's called truncation error. And truncation or discretization error comes from the fact that we are not exactly solving the equation that we want to solve. We're solving an approximation for it, or a truncation of it. And these errors always exist when in a numerical method, and they're usually the larger error. So a truncation error has two components. There's a local truncation error, and this is the error that is generated every single time step in the numerical solution. So if you think back to Euler's method, we had our solution, we know our solution at one point, we compute a solution at the next point. The error that is generated over that step is the local error. So the local error is the error generated every step. So it's just the error over one step. If we put all those errors together, we get what's called the global error. And this is the summation of all the local errors. So it's the error from all of the steps. And it's the error we really care about. So the global error is the error that we really care about. It's the error that really results in the end. If you compute what is the solution to your differential equation out to some time, the global error is going to tell you how far away your solution is from what you expect. The local error is only going to tell you how far away your solution is over the little time step that we have lots of those. So the global error is what we're going to focus on. So how can we get to this global error? Well, we're going to use the Taylor series to tell us how good of our numerical method is. So the Taylor series, you might recall, and if you have questions about the Taylor series, I'm going to post another video that explains the Taylor series in more detail. But the Taylor series is a way to expand a solution around some point, which is a little bit confusing, but we can write the Taylor series as y at some location I plus 1 is equal to y at some location I that we know plus the derivative of y at I times some step size plus y double prime at I over 2 times some step size plus a whole bunch more terms. We have as many terms as we want. yi to the nth derivative divided by n factorial times h to the n plus, and this series goes on to infinity. Now the cool thing is if we keep all the terms, the Taylor series is exact. So it's exact when all terms are kept. But alternatively, if we truncate the series, then we'll have an approximation to our function, and we'll know how far we are from the exact solution. So let's compare the Taylor series to Euler's method. So for the ODE, written as dy dx is equal to f of x comma y. This is the ODE that we solved when we were coming up with Euler's method. We can write this as y prime is equal to f of x comma y. Now if we plug this into our Taylor series, we can come up with the relation y I plus 1 is equal to yi plus f of xi yi, where I just plugged in f for y prime, times h plus f prime at xi yi all over 2 times h squared. And I just noticed I left off a squared when I was writing down the Taylor series. So I just added a squared in. Let me do that in red so you can see where I just added that in. Okay, so now going back down to the equation I just wrote, this is the Taylor series, and this keeps going on and on and on and on. But you'll notice the first little bit of it is exactly what we wrote for Euler's method. So if we look at this part of it, this is Euler's method. Now, what about the other terms in this series that we've neglected? Well, those are our error terms. So everything over here is the error, and the error, we know we now can quantify it. We can see that the error goes like this first error term. So if we look at these terms, the next term in this series, let me just write down what that is going to be. So the next term in this series is going to be plus f double prime at xi yi all over 3 factorial times h cubed plus dot dot dot. So these terms, we have h cubed, h squared, h cubed, h to the 4th, and so forth. And if we assume that if h is small, or h is much, much less than 1, then the first error term is going to be the largest. So then the f prime at xi yi divided by 2h squared term is the largest. So we know our order scales like h squared. That's another way of saying that. So the error scales like h squared. Or you could say the error is order h squared, which you can write that as the order of h squared. So now we know the error of Euler's method over one step scales like h squared. So that's interesting. Now, going back to our previous discussion, is this the local or the global error? Well, this is the error over one step, so this error is the local error. How do we get from a local error to a global error? So now we know the local error is order of h squared. Let's figure out how we can get to a global error. So the global error is related to the local error, and it's going to be the local error, let's just call that EL, times the number of steps, because it's the accumulation of error. And if we have the local error on each step, and we have so many steps, we multiply them together, we can get the global error. Now the number of steps we take is proportional to h. So this goes like e to the L times 1 over h. And why is the number of steps proportional to 1 over h? Well, if we have a solution that we're solving for over a distance L, and we break that up into a number of pieces, the step size h, as h decreases, the number of steps increases. So there's an inverse relationship between h and the number of steps. And if you could try this with L is equal to 1, and you let h is equal to a half, then the number of steps you have, say n, is equal to 2. If h is equal to a quarter, then the number of steps you have is equal to 4. So you can see that there's that relationship that I wrote up here is the same as what I wrote down here. So this is just a little example that shows this relationship up here. So now we know that the global error is the local error times 1 over h. So how can we use that? Well, now we can say that the global error is equal to our local error, which was order h squared, times 1 over h, which, if you put all that together, is equal to order h. That means the error that's the error between our numerical solution and our analytic solution should scale like our step size. So that means if we reduce our step size, our error should go down, and the relationship should be proportional. Let me just write that one more time down here. So let's say our global error is equal to the order of h. What does the result mean? Well, now that we know that the error goes like order h, we know that if we reduce the step size, the error will also go down. So if h decreases by some factor, then the error will also go down, and it will go down by the same factor, which is nice results because we know that we can control the error of our numerical solution now. If we want our numerical solution to have an error less than some threshold, we can compute what is the h needed to get us to that error.